the incident ray over here. And the reflected ray is right here. Everybody see that? Yeah. But it's hard to see this. I couldn't find the green laser for some reason. This is about the best I can do. There's also light being transmitted into the medium. If you're really close, you can actually see it. You can see the beam in the lucite, but if you're not really close, you can see it reflecting off the desk over here. That is getting to the desk because it's transmitted through the lucite and then out again over here. So at this boundary, we have both of these things. We have transmission up here, reflection up here, and we have transmission in the lucite here. Now, at those two boundaries, something different happens to the light. So we'll deal first with the reflection. If I were to draw what I just showed you, it might look something like this. Here is my boundary between media, I should say. So any two media will have different indices of refraction. So we'll say that this is N1 and this is N2. In other words, this medium has an index of refraction of N1, this one has an index of refraction of N2. The 1, 2 don't matter at all. I just picked it because this was first and this was second. It doesn't matter which one you call 1 and 2. And then I have a ray of light incident upon that medium. And I'll draw the reflected ray first. To characterize this interaction, we're always going to construct a line normal to the surface. We just call it the normal line from here on out. That's going to look like another chalk. It's going to look like this. So notice there is an angle, and this is always defined with respect to the normal. Please don't decide that. There's an angle here, which I'll call theta I for incident. There's an angle here, which I'll call theta R for reflected. Here's the easiest physical law you're ever going to learn in your lifetime. It's called the law of reflection. Theta incident is equal to theta reflected. Right? Not news to you if you've ever hit a bank shot in a pool. Right? Pool balls obey the law of reflection, assuming you don't have some crazy English on it, right? Because that can affect it. This is how you play bank shots in pool, right? You might have never quantified it, you might never have thought about it explicitly, but intuitively, if you've ever played pool, you know. You need to hit it. You need to hit a ball that's over here off of the bank. You pick a point right in the center of the two balls on the side, and you bank it from that spot if you have a chance. Right? It's because the law of reflection is the thing. Easiest law you ever. That's the law of reflection. Now, a couple things to notice. It was kind of hard to see. This is not a great laser. I'm not sure what's happened to all our nice lasers. I feel like they've wandered home, certain faculty members. I'm not among this game. The beam that was reflected, brighter or dimmer than the beam that was incident? Dimmer. Why? What does that mean? Well, first of all, let me say, that means it has less intensity. What does intensity make you think of? What is intensity in a wave paradigm? I mean, brightness, yeah. But what else? What's behind that? Energy. Yeah. The energy split. Some of the energy goes into the lucite. Some of it gets reflected. But the one that was reflected, what that means is the reflected ray has less energy than the incident ray, because the energy's been split. Now, we don't lose any energy. We can't allow ourselves that. Conservation of energy is still a thing. But it does mean that this has less energy than this one, unless this is perfectly reflective, and it's not. All right. Now, the light that was transmitted is like it was hard to see in the lucite. I'll try to bring a reto laser next time and show you. It actually appeared not to be traveling in a straight line, right? So if the light was going in a straight line, I'll put this as a dashed line. That would be my expected path, right? If there was no boundary there, the ray would just keep going straight because rays go straight. But that's actually not what we saw. It bent. It still looked straight. But in this object, it actually took a path like that. We say it bent towards the normal. Right? See what I mean? The normal line is here. If this was the original path, it bent towards the normal. That is actually a function of how the light is speeding up or slowing down. I will tell you right now, it might have been away from the normal if we were in a different situation. We'll talk about how to characterize those in a second. But for now, notice that this is a different angle. This I'll call theta t for theta transmitted. But theta t is not equal to theta I. And the relationship in general, not obvious just from looking at it, but I'll give it to you. It's called Snell's law, or the law of refraction. And it's this n1 sine theta 1 is equal to n2 sine theta 2. Where again, 1 and 2 don't really matter. But what we're saying is, if theta 1 is the angle measured in medium 1, that would be right here, you've got to match these two up. The index of refraction and the angle within the same media. Doesn't matter what you call 1 and 2. But they have to match. Okay? So this is, as long as you know the indices of refraction, you can measure one of the angles, you can find the other angle pretty easily. It's an inverse sine function. This actually turns out to be the case. This is true all the time. But this turns out to be the case when, let's do it. Let's derive it. We saw in this particular case that the light bent towards the normal. In this case, I'll write this down. This is not a general result, but in this case, theta transmitted is less than theta incident. Do we all agree that that's the case? Let's call, since I've already given you the subscripts, we'll call this the incident side and this the transmitted side. So I want to know what theta 2 is in relationship to theta 1. So let me solve for it. n1 over n2 sine theta 1 is equal to sine theta 2. Alright. The answer is right here. n1 over n2. Right? Bigger than 1, less than 1. You tell me. Let's think about it, right? N1, what is my medium outside the lucite? Air. What is the index of refraction of air? Remember, that's the lowest it's ever going to be, because that's the fastest light is ever going to be. We're considering air to be like vacuum, right? That's a weird approximation, right? Index of refraction of air and vacuum are the same thing, it's just 1. So in this case, I get a 1 over, I don't know what the index of refraction of lucite is, but I know it's bigger than 1, right? So I get over, 1. Don't write that down as lucite, I'm just guessing, I have no idea what it is. It's probably about right. But it's bigger than 1, that's what I know. So you tell me, bigger than 1, less than 1? Less than 1. Which means I'm taking the sine of this angle and reducing it. And that's the sine of my new angle. Now, sine goes as the angle, right? Lower the sine, lower the angle. Bigger the sine, bigger the angle. Think about it. Sine of 0 is 0. The sine of 90 is 1. It goes up as the angle increases. So does the sine. Cosine goes the other way, right? But as sine goes up, the angle increases. So if the sine of this one is less than the sine of this one, which is what this math tells us, it tells us that angle is smaller. It tells us we bent towards the normal. What does all this mean? It means if you're incident, I'll write this down too. I think I can erase this. When light moves into a slower medium. Slower than what? Than whatever medium in which it's traveling currently, right? Could be air, could be lucite, could be water, I don't know. If it moves into some other medium for which it's going to slow down, it bends toward the normal every time. Questions about that? Well, it can go the other way too. And you can prove it to yourself the other way if you draw this in the opposite way. Right? Let it bend away from the normal. Right? Maybe use lucite and air as an example. So let's if we were to do this, we would find this is the path of the light we have to take. As it moves back into the air, it speeds up. When it speeds up, it bends away from the normal. In this case, N2 is less than N1. You can run the math and prove it to yourself if you want to, or you can memorize it, or you can do both, which is the better plan. Right? If it moves from a slower to a faster medium, it bends away from the normal. So a lot of times we give you problems where light gets into air from some other medium. In every one of those problems, it's going to bend away from the normal because light is going to go fastest in air. So I can write that down. When light moves into a faster medium, faster than what? Whatever it is in which it's traveling, it bends away from the normal. Okay, questions about that? Okay. This leads to some interesting things, actually. It all leads to interesting things. If I didn't think so, I probably wouldn't be teaching this stuff. So, of course, I think it's all interesting. But this actually does lead to some really, really interesting phenomena. So, let's look at a situation. I will leave these equations up there. See if we can get some intuition as far as what's happening. Let's let this be the boundary between my medium, and this is going to be this is going to be this is a slow medium and this is a fast medium, right? And light is going to be moving from the slow to the fast. So here's my normal line, and I'm going to do one case in which light is just coming normal to the surface, or normal to the boundary. So in that case, we'll let this be 1, and this be 2. That's usually how I keep it straight. What is theta 1? 90 degrees, right? Oh, no. Sorry. My bad. 0, because we're measuring with respect to the normal line, not the surface, right? I made the same mistake you did at school. All right, in my mind. Yeah, it's 0. What's the sign of 0? 0. What's the only way this can be true if the left side is 0? What has to be true on the right side? 0. So N2's not 0, that means theta 2's got to be 0. So in this case, it doesn't bend at all, it just goes right. Now, let's move it over a little bit. I haven't moved it over much, just a little bit. Okay. Well, we know it's going to bend away from the normal. because we're moving from slow to fast. So here's the path that it would have taken, which means now it's probably going to look like this. And if you had numbers, you could calculate it, no big deal. But if you do this, you're going to find something interesting. So, in other words, I'm going to let this move over a little bit more. I actually find that the bending of the light in the new medium proceeds faster than the bending of the light down here, right? So I've moved this angle over a little bit, and I got a bigger return on my bending, right? I moved it over a little bit more, it bent even more. So as I move this over a little bit, the transmitted angle bends over a lot, right? A little bit, lot, a little bit, lot. What that means, if that's the case, then there is some angle for which I will send a ray incident upon this boundary, at which I can't bend over anymore. The light is just traveling perpendicular to the surface. Right? This will never happen if I'm going from fast to slow, because light bends towards the normal. This only happens if I'm going from slow to fast. Right? So this is the way we proceed. We start straight up, I get no bending. I bend over a little bit, the transmitted ray bends over a lot. A little bit more, a lot more. A little bit more, I find this particular angle for which the transmitted light is now going parallel to the surface. We call this the critical angle. And there is transmitted light, it's just traveling parallel to the surface. But the question is, what happens if I bend a little bit more? Right? Well, if I bend this over a little bit more, what would that mean for this? If I bend this thing even more, right now it's at a 90-degree angle, where would that be? And what would be here? Right? Still in the medium. Still in the medium means it didn't transmit. So that actually occurs. Now it doesn't bend over just like here because that's a transmission thing. Now I have reflection because it's still in the medium. What I get in that case, anything past this critical angle doesn't get transmitted at all. It's all within the medium. I get the phenomenon of total internal reflection. Again, this only occurs if I'm moving from slow to fast. I get this thing called total internal reflection. So here's, if I have this critical angle, right? I get a transmission angle of 90 degrees. Anything past that, nothing gets transmitted, it all gets reflected. And it gets reflected in accordance to the law of reflection. Right there. Right? It's a cool pick in your book of this. I gotta find it. There we go. And you can do this yourself. You have a pool at your apartment complex, go do some homework this afternoon and go to the pool. Right. So this picture is taken underwater of a little swimmer, right? Look at the top. What is that up there? What is this? Here. This is the top surface of the pool. Can you see out of it? No. Right. What you're seeing, well, the camera is situated. Well, okay, I should say, you can see out of it right here. You're just starting to see out of the surface of the pool, but you can't see out of it here. That's because the camera is sitting at an angle with respect to these points that is greater than the critical angle. Right? Right here, if I draw a line from the top of her head, right, to this point to the camera, and measure that angle with respect to the normal, that's the critical angle. Past that, you can't see out of the pool. This is total internal reflection. So you're actually seeing her back and the top of her head reflected in the surface of the pool. Go try it at the pool at your apartment complex or wherever you go swimming, right? Doesn't really work in lakes because they're murky. Swim down to the bottom and look up. Right above you, you can see out. Keep going far enough, and you stop seeing out. You just see blue. What is blue in the pool? Not the water. The water's clear. What's blue? Light. The bottom. You're actually seeing the bottom reflected in the surface. Like, you go down, it needs to be a little bit deep to do this. If you have access to a deep pool, if not, go to the Auburn City pool. It gets 14 feet in the deep end, right? Swim down to the bottom and look up. You can see out of the pool there, but as you move over, you start to see blue, just a ring of blue. That's the bottom of the pool and the sides being reflected from the top. You move past the critical angle. This is a really cool phenomenon. Most of us like cell phones and internet and Wi-Fi and all that things, right? We all day just transmitted through fiber optic cables now. What's a fiber optic cable? Well, it's a piece of really interesting glass through which they transmit laser pulses. You ever wondered how they transmit that around corners? Total internal reflection. Or at least mostly. There's some other stuff to go into that. It's really engineering. Really, really cool stuff. That's why if you've ever dealt with fiber optic cable, if someone hands you a piece of it, they say don't peek it, right? Because then you lose the total internal reflection. But as long as you keep your curves gentle, the light inside a fiber optic cable doesn't bounce, and there's a little bouncing, but it actually bends in the medium with total internal reflection. There's other things that go into it. It's not quite so simple, but this is a phenomenon that occurs. Some of you are married and you have diamond rings. Your diamond sparkles. Yeah? Why? Because light gets trapped inside a diamond and bounces around due to total internal reflection. Turns out diamond has the highest index of refraction of any naturally occurring material. It is to about 2.4, which means light slows way down. That's why they cut diamonds into all sorts of different facets, because you have a lot of total internal reflection. So light gets in the diamond, bounces around for a while before it gets out. Turns out, as white light bounces around inside a diamond, it splits up like it does in a prism, which is why your diamond rings will flash red and green and yellow. You're actually spreading out the light, and then some color gets out and you see it, right? It's all total internal reflection. It only occurs moving from slow to fast, right? Water is slow, air is fast. It doesn't work the other way. Diamond is slow, air is fast. It doesn't work the other way. How to calculate it? Any questions about it so far? Normally we're going to ask you to calculate the critical angle. How do we do that? The answer's right here. What is the transmitted angle? When light is incident at the critical angle, what's the transmitted angle? 90 degrees. What's the sine of 90 degrees? Therefore, by solving this,